Viewers of my channel who have seen some of the COVID-19 videos on restoring certain Heathkit test equipment, vintage test equipment that is, that has a particular resonance with me from my early days in electronics, will know that when I was a high school student in Germany, we had our entire new electronics laboratory outfitted with Heathkit equipment, which the students had to build during the summer before the first time the class would be opened. And I was starting to accumulate and or build a little bit of equipment while I lived there on a teenager's budget. You know, after all, most of the money I earned was earmarked for stereo equipment. What else? And you can only make so much money mowing lawns and so on. But I did have a bit of equipment. I had a power supply, although it wasn't regulated. It was just a rectified supply with a couple of taps. And I had another thing which was built off of a transformer from a Huey helicopter. And I had a meter that I designed and built, and a few other things. But due to weight restrictions coming back when we moved to the States, I had to dump all that stuff, along with a collection of vintage adding machines and mechanical calculators and things that I'd been collecting. And when I got back to the States and started or resumed college, I started trying to build up a new laboratory, and I acquired a Tektronix oscilloscope used that had been in the lab where my landlord, where I was renting a basement room from, his place was dumping an old Tektronix. All it needed was a power transformer, and luckily Tektronix warranted those for life. And they sent me a new transformer. I wired up, and I had a high-end oscilloscope for a person who was basically still, I don't know what I was, like 19 years old or something. And the first thing that I bought to be a piece of new equipment was a Heathkit IP-2728 power supply. This is what's pictured here, and the IP-27, or I'm sorry, the IP-2728 was a redesign, or I should say restyling, of the older IP-18 power supply, which originated in 1969 and was carried through 1977. And then they restyled it and gave it a new model number, IP-2728, and carried it all the way up until 1990. Its original price was about $22, and when they restyled it as the 2728, it went up to about $28. Of course, that's, in the money of those days, and it would be considerably more now, but these were low-end power supplies, but still, they were regulated, they had a decent amount of current, and they had things like current limiting, which was fairly sophisticated for such a small power supply. Really, the thing that was wanting on these is you didn't know what you were setting the voltages and currents to unless you had multiple meters to measure those things real time. Anyway, since I had long since, I think, dumped my IP-2728, a while back I had acquired one on eBay that was in very clean condition, and the previous owner had recapped some of it, and I went in and did a few tweaks and changed one more capacitor, cleaned a few things up, and then fully tested it. And this video is just my little nostalgic exploration of this piece of equipment. And if you're not familiar with it and have watched some of my other videos, then it can serve as an introduction to this classic power supply. So the IP-18 and IP-2728 had essentially two controls besides the power switch and a neon power on lamp. There was the voltage adjustment potentiometer at the left side, and this could adjust from roughly 1 volt at the low end or minimum to 15 volts or a bit more at the maximum. Again, it's a regulated supply, so whatever it was set for it would maintain, unless of course you reach the current limit, in which case the voltage would drop. To the upper right is the current adjust knob, and that could be adjusted down quite low and up to a maximum of 500 milliamps at the high end. Again, approximate. This was not calibratable. There were no trim pots inside, so it was all down to component tolerances. But essentially, you could have a full 500 milliamp maximum at anything from 1 volt to 15 volts or thereabouts, or you could limit the current to anything down to a pretty low value, you know, I don't know if it was 10 or 20 milliamps or something, but fairly low value. And if the current being pulled out of the power supply by the load, whatever you had it connected to, exceeded the current limit set point, then the power supply would automatically reduce the output voltage below whatever you had it set to, as required to not exceed that pre-selected current. The power supply used two different voltage references, one internal and then had the provision for an external voltage reference. And that's what this terminal on the back is, with a shunt jumper plate that could be connected between two screws or lifted off. In the default position, it's what is called AC. That doesn't mean that it's AC reference voltage. It just means it's using the AC powered internal reference voltage circuit as the reference voltage. Or if you open that jumper up and connect a voltage between 0 and 16 volts across the two screws marked DC, then that voltage would take place of the internal voltage reference. In either case, the voltage reference was then applied to the voltage control potentiometer on the front panel, and the result of that, depending on where its wiper was set to, would determine the actual output voltage of the regulated supply. Here's with the cover off. It's a single circuit board design with a few components that are not mounted on the circuit board. The circuit board is supported from the two control shafts of the voltage and current potentiometers. The potentiometers are actually on the circuit board, but there's these heavy threaded aluminum spacers going between those. These actually thread onto the threaded shafts of the potentiometers, and then go up to thread in turn into the front panel. So the circuit board is supported essentially off of the potentiometers. I think there may have also been a metal bracket that anchored the bottom of the circuit board to the bottom of the case as well. Here's a view of the circuit board from the rear of the power supply, and you can see there's about 4 electrolytic capacitors there, and another one on the terminal board on the back, and a couple of power resistors of various sizes, and otherwise a pretty simple circuit. If you look down at the lower left of the circuit board from this view, there's a couple transistors there and another one up towards the lower left, but it's really only set up with 5 transistors total, and one of them is in that black plastic cap mounted on the back panel of the power supply, so there's 4 more on the circuit board. And this photo also shows sort of a typically Heathkit kind of thing. Although normally their designs were as good as any commercial equipment and physically quite good with quality components and everything, this view shows a flying resistor, a 1K resistor, going from the circuit board and just flying through space, no insulation on its leads, and terminating to the terminal board of the back panel. There was no reason that I could see for that resistor to not have been on the circuit board. I don't know if they thought they were saving a wire or, you know, why they were doing that, but it's sort of an odd design decision. Also interestingly, on this product, instead of having wires soldered into holes in the circuit board, they use these little tinned metal sockets, if you will, that were soldered to the board, and then they're supposed to be used, I think, as sockets for individual wires. Like you could just plug a solid wire into them and then pull it out if you needed to later. But as I recall from building this, you were then supposed to solder the wire in. So I'm not sure what their thinking was there. Maybe they suspected that during the testing phase people would screw up a lot and would need to pull this out and would want the wires to come off. I really don't know. But I don't think that those wires were left just plugged into those little sockets. I think they were supposed to be soldered in there. Another Heathkit thing is the fuse here, which is in series with the power switch and basically right on the hot side of the power line. There was no fuse clip or fuse holder on the chassis or on the circuit board. Instead, the wire, it was just cut and soldered directly onto the end caps of the fuse, and this little insulating tube that goes around it in no way insulates the ends of the fuse, which if you cut the wire to the prescribed length and it was solid wire, it probably wasn't going anywhere. But boy, that's an awfully exposed AC hot right there for somebody picking this up. Your finger would naturally go there while lifting the case, and it looks kind of chancy to me. My guess is this originated probably with the IP-18, and they probably designed that originally to not have a fuse and then tacked it in later. To make sure that my tweaked and outfitted power supply with the final capacitors changed was working properly, I hooked it up to my electronic load and initially set the current to full clockwise, so about 500 milliamps, and the voltage to minimum, so roughly 1 volt. And you can see that here on the display of the electronic load. Here I've turned the power supply's volt adjust potentiometer up to full clockwise or maximum, and you can see here that it's about 17.8 volts that's actually being produced instead of the specified 15. And once again, it's trying to pull 50 milliamps from the supply, and it's actually getting 0.049, so 50 milliamps. Okay, the power supply is on. It's not going to put anything out because the current limit's turned down to 0. So I'm going to increase the current to full, which should be 500 milliamps. The voltage is minimum. I've got my electronic load here. Minimum is supposed to be around 1 volt. It's currently putting out 0.614 volts. The electronic load is set for 50 milliamps, and it's putting out about 50 milliamps right now at slightly less than 1 volt. If I crank her up to 15 volts, I can actually go up to 17.84. Let's just back it down a little bit. Let's say it's 15 volts. Pretty close. So that's about here on the knob. There doesn't seem to be any calibration in here for setting the voltage, so it is what it is according to resistor tolerances. So a little bit less than complete counterclockwise in the voltage control. I've got 15 volts output. It's programmed 50 milliamp load. It's putting out just a hair under 50 milliamps. And I'm going to lower the voltage knob until I get, say, 12 volts. Okay, that's about here. Still 50 milliamps. Now the way to set the current limit on this, since it doesn't have any meters or calibrated scale, is to, with the current all the way up, establish the desired load and then turn the current knob counterclockwise and watch the voltage. I should be able to turn it most of the way since 500 milliamps is the maximum. So I'm turning it down, waiting for the voltage to drop. There it started to drop. It dropped rather precipitously. I turn it up, now it doesn't increase the voltage at all as I turn it clockwise. I take it back just a hair, counterclockwise. and their voltage drops to clamp the current. Turn it just a little bit more clockwise until I get back to my 12.01. So that's my setting. Obviously, this is 50 milliamps, this is 500 milliamps. It's not linear. But anyway, it shouldn't put out more than 50 milliamps now. If I try to change the voltage up and down, the current will stay the same because I'm actively maintaining the current load at 50 milliamps. So I'm going back to about 12 volts here. And now I'm going to increase the current ever so slightly. I'm going to go up to, tell it to 55 milliamps, and the unit is putting out about 55, but the voltage is starting to drop. And now the voltage is dropping way down in order to produce the current I'm asking for, because I've got it clamped at what it thinks is 50 milliamps. So it's not terribly accurate, but the voltage is going way down, and I can't increase it beyond about 0.0, well, about, yeah, it's capping at about 60 milliamps. It won't go above that, even taking the voltage down to nothing. So as I reduce the current demand closer to 50 milliamps, all of a sudden the voltage recovers. It doesn't do it linearly, it just sort of snaps back. So that's how the current limiting works. It's not absolute, it lets me go slightly over, but it's basically working. Now I want to look at this with the scope and see if there's a lot of ripple on it. Okay, 2 volts per division, and I'm at 6 divisions, so that should be 12 volts, and that's what the load says it's putting out. I'm going to let the current control go all the way up to full. It doesn't change the voltage, and I can swing off the scale here back down to 12 volts, and that should be 8 volts, and it agrees there. 4 volts, 4 volts, and I can't go quite down to 0 volts. It should be limited to 1 volt according to the specs, but that would be about here, and I can clearly go slightly under that, down to, once again, around 0.65, 0.66 volts. Now let me bring it up to a nice median value. Once again, I'm going to say 8 volts, get it nice and centered. Verify that I'm at 8 volts, and now I'm going to AC couple the oscilloscope, and it's showing essentially nothing there, but I can reposition, get it up to the center, make sure that's still center, and now I can increase the volts per division. You know, there is a little ripple there, but it's a tiny amount. This is pretty darn flat. So this supply is working well. Interesting that the line fuse, in a kind of a kludgy way, is right here, wrapped with a piece of insulating cloth tubing right off of the power switch, but there's nothing keeping the side of the fuse from shorting out to the case, except that it doesn't currently. That worries me a little bit. Now, it probably wouldn't shift out of that position on account of you know, the wire from the power switch here is stiff wire and it's holding it in position, but still this is an unprotected side of the fuse at line voltage, and it's just hanging out here in space. Otherwise, this is the main pass transistor. Well, there is one other thing I can do with this. By removing this coupler on the back from the normal AC line powered reference voltage, I've decoupled that with this jumper, and now I should be able to clip on my signal generator here and cause the power supply to follow that voltage more or less. Okay, I've hooked up, I was hooking up my signal generator, but its impedance is incorrect for driving the very low impedance circuit here, so that wasn't working. It was loading it down too much. So I've got my bench power supply here, and it's putting out 15. Camera just does not like that color. It's putting out 15 volts, and I should be able to attenuate that with the voltage knob. It's fully clockwise now, and I'm at 16 volts showing on the scope. That's on the output of the power supply. That's 16 volts up there. If I turn the voltage knob down, I can take a ratio of that all the way down to about 1 volt. So we're up to about 16 volts here, and I get that with 15 volts here. So it seems to be taking the roughly 1 volt lowest voltage and then doing an offset to it. So 15 volts here is getting me, you know, roughly 16 volts on the output of the power supply. Let's see if that holds true. I can crank this down to, well, let's just take it down to 8 volts. 8 volts and see what happens. So right now I'm getting 8 volts would be on the center line. It's 1 volt above that. So it's tracking whatever the input voltage is here and adding about 1 volt to it and making that the power supply. If I wanted to reduce that a little bit, I could turn the voltage knob on the supply down and make this 8 volts as well. Now when I crank this up to 10 volts, it's 10 volts here, 12 volts, it's just about 12 volts there, 15, it's a little bit on the low side. I can tweak the voltage control, try to bring it right in line with that, but I think because it's an offset, not a strict ratio, if I take this back down to like 8 volts again, it's in the ballpark. It's a little bit high now, so it's not an absolute, but it does show that the output voltage of the power supply can be controlled by a voltage input to the terminals on the back. And then this control here is just basically taking an attenuation ratio of that. So that's working. Just a quick review of the schematic. This is one that was downloaded on a split sheet. I have a manual on order. It has the usual dual winding transformer power supply where the windings can be arranged in series or parallel depending on whether you want 220 volts or 110 volt supply. There's a power switch here on the fuse. The fact that the fuse is sort of jammed in here, and this is actually for, this is for the IP-2728. The IP, was it the IP-18? Is the original version of this, and this is just a restyled version with the same circuit, but the way Heath did things back in the period when that model was made, they were not putting fuses on the line side of a lot of their devices. So that may have been a small tweak that they just sort of jammed in there, and that may account for the fact that there's a fuse in such a kludgy position. We have 2 secondary windings. One of them is for the Zener reference voltage. half-wave rectification, small load, doesn't need a lot of filtering. Then there's a zener and a resistor to knock it down to 20 volts. And then another resistor and another capacitor to filter it some more. And then that is assuming you've got the jumper in the AC position, which does not mean that there's an AC voltage applied. It's just meaning that the reference voltage that's being used is the one coming off of the AC line instead of a DC source coming from somewhere else. That is applied across this potentiometer, which is the voltage adjust here. It's only 5,000 ohms. If the jumper is removed there and the jumper is put here, you apply, roughly the same voltage as the output can be, and then that is, the minus side is put to here, the plus side is put to here, and you just pick off that voltage, that input voltage with the potentiometer, and that's roughly 0 to 16 volts. The positive side of this zener supply is common with the positive output, so it's referenced on the high side of the circuit. The wiper of the potentiometer goes straight through a diode into this NPN transistor, which I think is an error sensing transistor. Its emitter is common with the negative output power of the power supply, so as the voltage using the plus side of the power supply as reference, if the negative terminal is at roughly the same voltage as this, then it doesn't do much. But if you have a difference between the reference voltage selected by the voltage control and the actual voltage on the output, then it'll progressively turn this transistor on more. And there is a power supply winding here with a center tap. The center tap is just circuit or output ground. Then there's a split transformer full wave rectification, but it's not a full wave bridge. And then it's filtered with a 2500 microfarad capacitor, then another resistor capacitor to filter it some more, and it's applied to the output stage. This appears to be probably a constant current reference through this FET, providing a constant current through this transistor to circuit common, and therefore the amount that this conducts would determine the voltage here. Here's a Darlington amplifier with the power transistor on the back and a smaller transistor internally driving the base of that. So this is the series pass transistor and its driver, and then that conducts as required to keep the requisite output voltage. And then there's the current going through a shunt, which is comprised of the 100 ohm current potentiometer and a 0.51 ohm shunt resistor in series with it. And you essentially get a voltage dropped across the shunt resistor. And if that gets high enough to turn this transistor on, then all of a sudden it starts conducting and it's shorting this point to this point, and that's where the current is being clamped down. It just reduces the voltage until you get a current that doesn't turn the transistor on more. And then there's a final filtering cap on the output and a 3300 ohm load resistor across the output.